In this video, we'll be talking about balancing chemical equations. Here are our objective and essential question. Again, as always, I encourage you all to pause the video so you can write both of these down in the top of your notes and continue on throughout the video, pausing when you need to record whatever is on the slide whenever you see this handwriting icon in the top right corner. Our objective today is to be able to define and balance a chemical equation. And our essential question is, how do we balance chemical equations to describe a chemical reaction? So you should use this essential question to try to answer this essential question in the summary at the end of your notes from this video today. So let's talk about what a chemical equation is. A chemical equation is a symbolic representation of a chemical reaction that uses the chemical formulas of compounds and pure elements. So in this case, what this chemical equation is showing us is it's basically a shortened recipe for creating the products of this chemical reaction. So what this is showing us is how to make table salt by reacting sodium with chlorine to get sodium chloride. This equation is showing a different chemical reaction. It's showing the reaction of zinc to chloride and hydrogen to create zinc, the metal, and just the pure metal, and hydrochloric acid. So if we were to break the parts of a chemical equation down even further, we have our reactants, which are typically going to be on the left side of the arrow here. However, not always. And those reactants are elements or compounds that go into a chemical reaction. Think of the reactants as like ingredients. You put ingredients into a recipe to make a cake. You put the reactants into a chemical reaction to form a chemical product. Now, our products are what comes out after a chemical reaction has occurred. And while the products are typically going to be on the right side of that chemical equation, not always, but what is always true is that the arrow in the chemical equation will always point toward the reactants. So if you think back to when you did input and outputs in math classes, our input is always going to be our reactants and our output is going to be our products. Now, the coefficients in a chemical equation describe the amount of the pure element or compound in the reaction. And we have actually already learned the typical unit of measurement to measure the amount of those going into it is moles. So what this 2 is saying in front of sodium here is that 2 moles of sodium are going into that chemical reaction. So we've talked about what a chemical equation is. Now let's talk about what a balanced chemical equation is. Now, a balanced chemical equation is when the number of atoms of the elements in the reactants are the same as the number of atoms of the same elements in the products. So for example, here we've got our sodium and our chlorine coming together to form sodium chloride. If I count up the number of sodium atoms, I see I have 2 sodium atoms on the left side of the chemical equation, and I have 2 sodium atoms on the right side of the chemical equation. So look at the arrow that kind of divides both sides of the chemical equation from left and right. And you just will be counting up the number of atoms of each element to make sure they match up on both sides. So just like sodium, chlorine is also balanced here. We have 2 chlorine atoms on the left side, and we have 2 chlorine atoms on the right side. Now, these may be mixed up and forming different compounds, but fundamentally, we still have the same number of atoms. The basic unit of any compound is the same for all the elements on either side of that chemical equation. You can also look at zinc chloride or zinc 2 chloride, excuse me, and hydrogen, right? We have 1 zinc here in purple. We have 2 chlorine atoms on both sides, and we have 2 hydrogen atoms on both sides. So the main idea is when it comes to balancing chemical equations or a balanced chemical equation. I'm going to run through these and use this chemical equation as an example. So the law of conservation of mass tells us that we cannot lose or gain atoms from what we start with. So whatever atoms we are starting with here on our reactant side of the equation, we have to have the same number of atoms that we finish with. That is what the law of conservation of mass states. But the identity of a compound is dictated by its proportion of elements to each other. So for example, CH2 is a very different substance from CH4. So the ratio of the elements to each other in a compound dictates specifically what that substance is and its chemical and physical properties. So just like in this example, right, table salt is NaCl. Okay. Na2Cl2, that's not table salt anymore, even though it still even has the same ratio of sodium and chlorine to each other. That is not table salt. So finally, since the proportion of elements dictates the identity of the compound, we have to adjust the moles or the amount of the reactants and products we have to make sure the number of atoms are equal on both sides of the chemical equation. So our moles are our coefficient, that's our big number here. So if we can't change these subscripts, we can at least change the amount of that element or compound going in or out. So we're going to watch that play out on the following slide. Again, this was a lot of writing, but it is important concepts that I would like to see in your all's notes. So I encourage you all to pause the video, give yourself time to write these down, and then resume so we can go on to the next slide. Okay, so these are the steps we're going to follow to balance chemical equations. And again, please do pause. I recognize this is a lot of writing for your notes from this video today. So please do pause and try to take some time to write down these steps before moving on and playing the rest of the video. So our first step is to make a T-chart below the chemical equation and draw a line separating the reactants from the products. So I like to find that arrow in the chemical equation, and I'm going to draw a line to separate our reactants from our products. So our reactants, again, are facing away from the arrow, and our products are always in that direction that the arrow is pointing. So that's step number one. Step number two is writing the elemental symbol for all elements you see on either side of the arrow. So I see a sodium here, and I see a chlorine, and I see a sodium again, and I see another chlorine. I'll give y'all a hint. If you ever see that your reactants and your product's elements are not matching up, if you were to have a random element over on one side and not on the other, that is an indicator that you have already made a mistake, because the law of conservation of mass states that these have to be the same elements. Okay, step number 3. And I'm actually going to quickly erase these circles over here so this doesn't get in our way of seeing that chemical equation. Step number 3 is to count the number of atoms for each element and record. So if I'm counting right now the number of atoms of each element, so right now I don't see a coefficient in front of Na or in front of sodium, so I'm going to write a 1 for sodium, because no coefficient means we just have one of that thing. And I don't see a coefficient in front of chlorine, but I do see this subscript. Remember, whenever time you see a subscript, that still indicates you have 2 atoms, or however many atoms that subscript is. Okay, so I see 1 sodium and 2 chlorines. Now on this side, I see 1 sodium again, because there's no coefficient. And I see 1 chlorine. There's no coefficient in front of chlorine as well. And there's no subscript here. This is empty. So this is telling us that in the sodium chloride, there's 1 sodium atom and 1 chlorine atom. Okay, so that is step number 3. You can check that off. And finally, step number 4 is to change the moles, the big number, or also called the coefficient of each element or molecule on either side until both sides have the same number of atoms of each element. Now, this step is going to entail a lot of just moving back and forth between the 2 sides. So we're going to watch that play out right now. So looking at our reactants in our products, I'm going to first evaluate sodium, and I see that sodium is equal on both sides. However, if I look at chlorine, I see that chlorine is not balanced, meaning that there are more chlorines over here on the reactant side than there are on the product side. So I need to do something about that. Now, what I'm going to do is I'm going to change this number to a 2, but when I change this number to a 2, that's not doing anything to my chemical equation. So whenever I make changes down here, I also have to remember to make changes up here. So I'm going to plug that in the blank for the coefficient in front of sodium chloride up here. So now I have my sodiums. But since I put a 2 in front of this sodium here, what this is actually doing is now this sodium becomes a 2. So I have to make another adjustment over here. Well, my chlorines are all balanced out, so I'm good there. I don't need to make a change for this chlorine, but I do need to make a change in front of this sodium. So in order to balance out 2 sodiums on the product side, I'm going to have 2 sodiums on the reactant side. So I'm going to add a 2 in front of that sodium there. And that gets me my final balanced chemical equation. And I'll rewrite it up here just so you all can see again. So it's 2Na plus Cl2 to get a product of 2NaCl. So 2 sodium atoms plus 2 chlorine atoms, or a molecule of chlorine, yields 2 sodium chloride molecules. So hopefully that helps and these steps make sense. And I look forward to discussing this in class with you all next time.